Hi, everyone. This is Sergey. He is a software engineer, a big fan of the JVM platform, distributed systems, and functional programming. Sergey has previously worked at Nauman, JetBrains, and Sergey has joined the infrastructure team at Canva in 2016 and has helped Canva services scale to a state where they can reliably serve tens to millions of users. So please, let's welcome Sergey for his next presentation. Thank you.
Hello, everyone. Here's Canva. Canva is a design platform where you can design pretty much anything: social media, presentations, posters, or even a birthday card for your favorite programming language. And like with many other systems, a lot of the interactions with Canva can be represented as request response. For example, as a user, you can type some text into the search field, and that'll be a request. And the list of the templates that you get back is the response. Or if you click on a template, that's a request. If you update, and the updated document is the response. If you edit the heading, that's a request, and the saved document is the response. But the game changes completely once the second user joins the editing. You want to see the changes that other people are making immediately without explicitly requesting them. If the second user types anything into the search field, or even updates the template completely, you want to see the effects straight away to avoid any possible conflicts. My name is Sergey. I work on the gateway team at Canva. And some time ago, our team set off on a journey to build a platform to support real-time services to enable our users to collaborate with each other. And real-time is quite an overloaded term. So to be more precise, it's soft real-time. So let's take a look at what exactly I mean when I say real-time. Imagine two users, Alice and Bob, and they both want to edit the same design together at the same time. Alice wants to make a simple change to add an exclamation mark. And Bob needs to see the change as soon as possible without sending a request and asking for these changes explicitly to avoid any conflicts. And there are many properties such a system could have, especially around reliability. And fundamentally, there are two sets of properties. The first one are application properties. And they contain everything that application is concerned about. It's the protocol, timeouts, rate limiting, everything that belongs to the application code. And the infrastructure is all about running the app. It's load balancing, it's infrastructure, it's alerts, it's how we auto scale, it's everything about how we run the app. And many of these properties are very similar between these two types of applications, between request response applications and streaming applications. However, some of the aspects are very different. And at Canva, we had to come up with a solution for every single such a difference. And these differences is what I'm going to focus on today. So let's start from the application, and in particular about the protocol. There is a number of ways to implement the protocol, and long polling is more or less the classic one. It's been around for a while. It's an old and well-understood technique. And the idea is that Bob would send a request every now and then, and the server doesn't respond immediately and send a request back. The server holds the connection, but once the data is available, the server sends a response back to Bob. And then when Bob receives the data, he has to make a request again. And while you could implement a real-time service with long polling, it's not really widely used anymore. First of all, there'll be latency issues. Bob has to send a request every single time after getting a response. And there could also be issues with state and concurrency. How to ensure that there is only one request at a time from Bob, and how to ensure the order of the messages between different requests. And there are many of questions like this, and just the list of these questions goes on and on and on. And with the wide adoption of HTTP2, there is also an alternative. It's server-side events. And while technically you could implement a streaming service with server-side events, there'll be some problems. First of all, server-side events are not really supported by layer 7 load balancers as much, and we use them actively. But even bigger issue is that it's only one-way channel, and they require building another protocol in order to make it a bidirectional abstraction. And WebSockets are a perfect transfer for this use case. They provide an abstraction which is very similar to normal sockets. It's bytes in, bytes out. And on top of these, WebSockets are supported by all of the modern browsers and servers. Okay, so WebSockets are great. And it's relatively easy to implement message passing for a single service. Just take JSON payloads, encode them as bytes, put them into WebSocket frames, and send them to the backend. It's that easy. However, there are many pieces of functionality that need to be as close to real-time as possible. For example, there could be a second server, the commenting server, or notification server, and adding a second WebSocket connection from the client would double the load on the backends. And adding a third service, let's say to handle analytics, would require another connection. And I think you can see the challenge here. Adding every single new service would require us adding another connection onto the clients, effectively increasing the load. So in order to avoid this, we have to perform multiplexing of different channels within a single connection, of different backends within a single connection. And that way, the number of connections will only grow with the number of users and not the number of backends that we need to support. And the most straightforward way to implement this functionality is to implement something like a WebSocket gateway. And the WebSocket gateway could be this backend that accepts the connections from the users and forwards the appropriate messages to the appropriate backends. So basically, Bob puts all of the messages editing and commenting into the same connection. The WebSocket gateway unpacks them and sends the relevant messages, the red ones to the editing service and the green one to the commenting service. And as a gateway, it could also perform all of the other infrastructure functionality, such as authentication, authorization, logging, tracing, what's not. However, you can't just take different payloads and put it inside the same connection. WebSocket needs to understand which backends these messages belong to, and there needs to be some another protocol. And WebSocket by themselves don't provide this level of abstraction. It's just a transport protocol. It's not an application protocol. So we have to invent another application protocol on top of this, on top of the connection, on top of WebSocket, so that we can differentiate between different messages. And luckily for us, there is such a protocol already. RSocket provides a way to multiplex multiple streams over a single connection, and it provides a programming model based on channels. And the biggest difference between RSocket and any other protocol is that it provides us with a reactive stream semantics over a network. What does it mean? So reactive streams, it's an initiative that defines how stream processing can be done across multiple runtimes. And the key part of this initiative is the standard for handling non-blocking backpressure across multiple streams. So let's take a look at what this means on a practical example. Okay, here is Bob again, who just established a WebSocket connection to the WebSocket gateway. And within this WebSocket connection, Bob can open multiple channels. For example, Bob can open a commenting channel and a channel for the editing service. And RSocket can take care of creating and managing these channels and ensuring the order of the messages within those channels. And what's really important, that every single channel has its own backpressure semantics. And backpressure is a critical part here. So let's zoom in onto one of these channels, for example, onto the commenting channel, to understand how this helps us. Okay, here is Bob, who is the requester in this interaction, and WebSocket gateway, who is the responder. And once the Bob established the channel, Bob doesn't start sending messages just yet. It's the responder who starts the interaction. So the responder sends a message that says, I am ready to accept 5 messages. After that, Bob understands that Bob can send 5 messages. And he starts sending messages one by one. The first message, then the second message. And at this point, Bob knows that it can only send 3 more messages. Another message. And at this point, Bob knows that he can only send 2 more messages. But the responder, WebSocket gateway, also keeps track of this. So it sends a request to get more messages concurrently. And the key part here, that it doesn't block Bob from sending messages. It happens concurrently, so it's not blocking. And that way, Bob knows that he can send 4 more messages. And the interactions flows in this way, allowing for sending Bob more messages and for the WebSocket gateway to accept them. And the key part of this, the key takeaway, is that the responder, WebSocket gateway, has to request messages every now and then in order to continue receiving them. So what does it give us exactly? Consider a simple stream implementation with no backpressure at all. Most of the time, it's going to work exactly the same. Red messages flow to the editing service and green to the commenting service. But it's an outage that makes the difference. It's never possible to avoid outages completely, and it's a question of time until an outage occurs. And without backpressure, there is not much that you can do. If the editing service is down, the messages will start piling up, and the clients won't stop producing them. They will continue sending more and more and more and more. And that way, the outage can not only bring the whole connection down, it can put down the whole gateway and the editing service, and it's not a very good situation to be in. One service is down, the whole system is down. And backpressure with RSocket saves us here. If the editing service goes down, it will stop requesting messages, and the clients will stop producing them. So the messages will be flowing through the gateway to all the backends successfully, and it's just that one service which is having issues will be unavailable. And compared to the standard techniques like circuit breaking, there is no need to enter the error state even. There is no need to reach this error situation for the mitigation to kick in. We don't try to fight ourselves. If the server requires messages, it will request them, and it's that simple. If the server doesn't request messages, the clients won't be sending them. And the idea sounds amazing, but what about the implementation? All of our backends run on Java, and there is an amazing implementation of RSocket on JVM. And RSocket Java as a library comes with a server that's built on top of Netty. But if you're already using some other server, like maybe, for example, JT, you don't have to give up all of the knowledge and all of the observability and monitoring setup that you've already acquired over the years. You can just implement the transport. You can integrate RSocket Java pretty much with any server. You just need to implement an interface, transport interface, that says how to send the messages and how to receive the messages. And that's basically where to get bytes from and where to send bytes to. And the second part is to implement an acceptor. An acceptor is how you're handling the input. And in the acceptor, it's basically the implementation of the request channel. RSocket supports multiple interactions, request response, or fire and forget. But for us, at least, the key part here and the most generic protocol is the request channels that receives a set of incoming messages and provides a set of outgoing messages. And for the incoming messages, you can subscribe onto them and implement 3 operations. What do you do when the message arrives? What do you do when the stream completes? And what do you do with the error, if an error occurs? And for the outgoing messages, you just send them. And it's pretty easy to handle it in that way. However, if you implement a service that's just using subscribes and using this standard set of interfaces, then you might lose some backpressure along the way. And it's very hard to actually handle the streams and build big applications on top of these. And RSocket is just network abstraction. There also needs to be a library for handling the streams. And Project React is that library that's also used by RSocket. And it's a hugely beneficial library, as it provides you with all of the set of operators that you need to use in order to successfully implement an application. It's map, filter, and all of the others that are very hard to implement if you want to support backpressure. And the library just provides you these operators for free, and you can implement business logic using them. And this paradigm of reactive streams was proven so useful that this set of interfaces was even included into the standard library in JDK 9. And on the front end, it's practically the default for building interfaces nowadays. A lot of front-end engineers know this library, RxJS, which provides you with the abstraction of reactive programming using a very similar set of interfaces. But here comes a surprise. RxJS does not support backpressure. So instead, RSocket.js comes with its own set of classes that do support backpressure. And the decision of RxJS engineers to not support backpressure is totally understandable. There is not much backpressure you can apply to a user. If a user is typing on a keyboard, and RxJS is mostly used for building user interfaces, you can't really apply backpressure to a user. So another challenge here is to take RSocket flowable, which do support backpressure, and convert it into observables. Because basically the whole ecosystem of the frontend knows about RxJS, but doesn't really know about the interfaces of RSocket. And there needs to be some conversion between these two interfaces. And that's a great place where you can decide on your backpressure strategy. How exactly your app is going to react when your servers are down. And the great thing that you can decide this on a per channel basis. For example, if your analytics service is down, then you can say, my backpressure strategy will be to buffer messages for a while, but once it reaches a certain number, just start dropping them. Analytics is not critical. But if your editing service is down, you want to stop users immediately as soon as you notice that, because you don't want users to lose any data. You want to stop them and show like some error message. Please stop editing right now. And backpressure is great when just one of the backends is down. But there is always a risk that the whole WebSocket gateway goes down. In that instance, like an instance might get restarted or anything can happen in the cloud. So in that case, the clients need to reconnect. And that's the part of the code that needs to be implemented really carefully. The very first thing to consider is to implement exponential backoff. You don't want the clients to constantly try to reconnect, but rather increase wait times if the server does not respond. For example, try after 2 seconds, then try after 4 seconds, then after 8 seconds, then again after 16 seconds, until you reach a certain limit. But when implementing exponential backoff, it's also very critical to implement jitter, because when your servers are finally up after an outage, the last thing you want to happen is for all of these clients to come into your application at exactly the same time after 16 seconds. And jitter helps to avoid this by adding randomness. That way, some clients will come to you after 13 seconds, some clients after 20 seconds, but they won't come all together at the same time, just smashing your backends. And I hope it's clearer how you can implement the application in that way. So let's now take a look at the infrastructure concerns. And the very first and very critical part of any reliable infrastructure is load balancing. So here's our architecture. Users are connecting to the WebSocket gateway, and the gateway connects to the downstream backends. And on these diagrams, you can see the connections of two types, of type 1 and type 2. And the connections of type 1 are the users that are connecting to the gateway. And we have as many connections of type 1 as we have our users, because every single connection represents a user identity. It's that connection with the attached cookies, with all of the user metadata. And the connections of type 2 are the connections between two backends. And we don't have to have as many of them. Even a single connection between the WebSocket gateway and the backend can be enough. And that's another important part, another role of the WebSocket gateway, because it takes care of handling a large number of connections, because it's not something trivial. You have to configure your servers in an appropriate way. You have to have enough memory to have all of the metadata about the connections in memory. And that's basically another role that the gateway is performing. And the load balancing of the connections of type 1 is pretty easy. Every time a new user comes to you, if you're using some layer 7 load balancer, you can just choose a gateway and proxy the connection there. But load balancing the channels across between WebSocket gateway and the backends is a bit more tricky. And our first idea was to load balance them in exactly the same way using layer 7 load balancer. So we could have a gateway, we could have a load balancer in the middle, and multiple targets behind this load balancer. However, we quickly discovered that it doesn't quite work as well as expected. consider the situation when the load increases and the load on the backends crosses a certain threshold. So it's time to scale up. It's time to add a new instance. And the new backends start, but don't receive any connections at all. So why's that? And the reason is that the WebSocket gateway doesn't even know about that backend that has just started. It already has enough connections to to existing backends, and it just continue creating more and more channels across these connections. Because with RSocket, we can create as many channels as we want across a single connection. And as a result, these backends continue getting overloaded, and the whole scheme just doesn't work. So that can be resolved by ensuring that every single gateway connects to the backends directly. But that means that the gateways need to know the addresses of the backends. And that can be solved with an introduction of a service registry. That way, every single time a new backend starts, it registers itself in the service registry. And the WebSocket gateway listens to the updates from the registry and establishes the connections to the backends directly. And what's important now that every single gateway is connected to every single backend, it can do proper load balancing because it knows the number of channels that are created across every single backend. And it's important to note that the classic round-robin algorithm doesn't quite work well in that situation. Consider the situation where a new backend has just started, and it only has one channel with the WebSocket gateway, whereas the existing backends have about 10,000 channels. So if we continue doing round robin in that way, we will still be sending a lot of traffic to the existing backends. So instead, we could rely on a list loaded algorithm as a reasonable choice in order to start creating new channels to the backends, because when the channels are long-lived, again, the game changes. And another crucial part of the reliability strategy is for the gateways to scale up under load. And the load for the gateways, or for any service that accepts a large number of connections, is often defined by the number of connections and not, let's say, CPU. And that might not be true for every single load pattern out there, but for the WebSocket gateway, it's likely to be true. And it's very important to consider this when doing load testing. And when you're an engineer and you're writing a load test, it's very compelling to create a load test that sends 1 megabyte payloads every 100 milliseconds. And in that case, yes, indeed, you're likely to run out of CPU first. However, for many real-world applications, a lot of the connections will be idle. For example, there can be a connection in the browser, but user might not do anything or do something infrequently. But the backends will still have to handle all of these connections. So in that case, you might actually run out of memory first, or a number of file descriptors. So it's very important to scale a proper auto-scaling target. And in that case, it could be a number of connections. And as a secondary, as a fallback, it could still be CPU. But no code stays the same forever. And deploying often, at least daily, it's practically a requirement for any modern software. However, redeploying an instance that maintains a large number of connections can be a challenge. So what is redeployment? In its essence, it's about replacing the whole fleet of old instances with a set of new instances. And doing the same very sharply can result in a huge spike in latency and errors on the graph. And you still have to survive sharp reconnections quickly because, for example, one day your services might go down briefly. And in that case, all of the clients will have to reconnect. And it's important to survive such spikes, but if possible, it's better to really avoid them during normal redeployments because redeployments happen really often. And the typical way to handle this with request response application is to use something that's called a deregistration delay. So that means that at some point in time, when you attach a new fleet, the load balancer will start creating all of the new connections and sending new connections to the new gateway, and the old connections will normally die. And that works quite well for request response paradigm. But with the long-lived connections, they just don't die. They still stay attached to the old gateway for a very long time. And in that case, the application has to take care of this itself. It has to, at some point, start killing the connections or asking the clients to close the connection in order for the clients to reconnect to the new fleet. And at least if you're on AWS, it can be quite tricky, but it's always possible. So in that case, the application needs to take care of the shifting the traffic manually. And every single time a load balancer is being deregistered, there can be some event. And in AWS, you can listen to these events, and you can route them to some piece of software like a Lambda function or another application that can actually inspect the event and understand which particular instance is about to be deregistered and destroyed. And then you can notify that application in some way, and the application will start killing connections or asking the clients to reconnect. And that way you can successfully deploy and enjoy these beautiful graphs where the load is shifted very, very gradually and not very sharply. And in conclusion, you can build real-time streaming services, but many of the controls and reliability features are going to be drastically different between the request response applications and the streaming applications. And building such services is definitely, it is a hard task. It's hard, but it's absolutely possible, and it greatly improves user experience. And with such an amazing set of libraries like RSocket Java, it's not actually that hard of a task. It helps a lot. So I hope that information that I showed you this to you was useful to you. And that's the end of my talk. Thank you.